You write into the memory first. Write into the memory. All these are small piece of data. You write into the memory. You don't write into the hard disk. Once you finish, let's say 1 megabyte here. Finish 1 megabyte. Then one time you transfer this 1 megabyte. So one access rather than multiple accesses, because multiple accesses will be slow. Okay? So one access is much better. Because hard disk also, when it's stored in a form of segment. Okay? Segment of 64 kilobyte. Okay, so when you send one segment of 64 kilobyte, or we call sector. One sector. That sector on a plate, on the hard disk plate, there is one sector. There's one sector. So when you write the whole 64 kilobyte sector into this plate, the hard disk plate, and it's more efficient. It's faster as well. Okay, so it's still accessing I/O many times. You access one time, and how do you do it? You have to sacrifice your memory. Let's say 1 megabyte of memory or 64K. You write until you fill in all. Then one time you transfer. Okay. The same thing for the fourth advice, which is fewer larger files perform better than many small files. Basically, the same thing is talking about this as well. So one big file rather than small files, many small files. Okay, another thing is this. For example, here, I told you that, let's say, for example, you have no choice, right? You only have one hard disk, you don't have multiple hard disks like this. You got only one. And here you got multiple processors trying to access this hard disk. Okay? So it is going to wait for one another. So it's going to be bad. They're going to race with one another. So we have to use mutual exclusion to access into this hard disk. So everybody will be blocked except one at a time to access this data. What we can do is, perhaps not like this, you do like this. You're going to access this data by only one process. Let's say root process, root is 0. And then this root is going to help read the data and then transport to all. Sorry, scatter better today. Okay, you scatter to all here. So here you don't have to worry about mutual exclusion here, because there's only one process accessing this. He's the sole person access this. So there's no need for waiting. Right? There's no mutual exclusion. So this guy is one process. His job is going to read the data for all, and then you scatter it. Okay? So confine I/O to specific serial portion of the job basically means this. Okay, whatever that is written there is actually talking about this. Okay, the last one, the same thing. Actually, it's the same as what the first one is talking about. If let's say here, because you have the data, you want to distribute or share, right? But there's sometimes they have data to store. They don't access into this secondary storage themselves. What they do is they pass to this middleman. Okay, everybody wants to access. You have to access to this middleman. So you pass the data to this middleman, and this is only one process again, and he has the sole access to this hard disk. So he's going to write on behalf of the task. Okay, and this can be very fast because while you're writing, I can just send to you. I don't wait. But you're busy writing. Let's say process 0 is writing for process 1. Process 2 need to write, right? So I just send the data to you, and then I can go off and do other job. Provided that I'm also running in asynchronous mode. That means I don't wait for you. I send in asynchronous manner, and then I can proceed to do my job while you're busy serving this guy. Okay? Once my turn comes, he will write into it, and then I can check the status later. Okay? So these are the possibility that you can do in order to increase the paracomputing because of the problem that we face, right? Because of physical limitation, you have to find a way around it. Now we are moving on to a different topic. Right now I'm going to talk about GPU. Okay, the GPU can solve a matrix very efficiently because actually GPU is meant for 3D graphics, and 3D graphics, all your graphics actually are converted into matrix before they do the computation. Okay, and the graphics use 3 dimensions, so that's why your GPU has X, Y, Z. Okay, but then of course it's flexible enough to compute arbitrary amount of dimensions, not only 3 dimensions. You can reuse it many times in order to compute multiple dimensions. Example, if you do AI, the matrix is multiple dimension. Okay, so but you still can use GPU to solve the problem. Okay, because it's not just for 3D only. Okay, in this matrix they have only 2 dimensions. Now how does the track works? Okay, I always find that this is very confusing. Actually, when I learned this, I was also confused in the first place because I'm new to this GPU also. But then after a while, I get used to it. You have to think differently when you look at this program. We always deal with 1 dimension, so it's quite easy. The reason why we use the ID is because single program, multiple data, right? Every of the thread is going to run this single program. Okay? But the data is going to be different, right? But how do you differentiate who actually do which data? So that's the question, right? So the data, you've got a lot of data here. Which thread do which? Of course, we know that all of them will run this program, so there's no distinction. We don't need ID to find out who run which code, all right? Because it's a single program, multiple data. But we have a problem here. Which data we assign to the thread? The easiest way, of course you have many ways, the easiest way is to use the ID of the thread. Okay, and the data is in sequence, right? We can label this as 0, 1, 2, 3, 4, and so on and so forth. Okay, the easiest is thread 0 to data 0, thread 1 to data 1, thread 2 to data 2, right? And so on and so forth. But we have a problem here. If let's say our data is quite huge, let's say 1 million here, but our thread ID is only 16, so we have to repeat that, right? So we have something like 16, so here is 15. And thread ID 15 is supposed to do this, okay? Now because we've run out of the thread already, but we can repeat this, right? Okay, we can repeat this. It means we can reuse this thread to do this other data, 16, 17, 18, and so on and so forth. So here we're going to assign to 0 again, assign to 1 again, assign to 2. Yeah? Now because of this, that's why we have 4 loops. This is the first loop, loop number 1, loop number 0, sorry. This is loop number 1. Okay, and if we have more data here, we have to loop multiple more times. But of course, the number of loop is less than the number of data. Okay? If the number of data here is n, the number of for loop is actually n divided by number of threads. Okay? So you've got 16 here. This 1 million divided by 16. So that's how many loops that you have, because each loop you process this in parallel, but in between these two in serial. So here process in parallel. Okay, so this one is process in parallel, but in between here process in sequential, again in serial. After this one finished, then only you can move on to this. Okay, so there's a limitation if you use both. Right? But one thing good about this GPU is actually it has this problem also, but it's hiding behind this whatever formula that you see there. Because in GPU, we have another terminology, additional terminology. What we learned here is just a track ID, right? In MPI, OMP, and MPI. We only got track ID, and that's all. But then in GPU, we have another one, block size, grid size. Okay, so we got block size. Okay, and then inside this block grid, we have blocks. So this is block 0, this is block 1, this is block 2. Okay, in OMP and MPI, there's only block. The equivalent to it is block. Okay, and inside here is the track. All the track live inside there. So this is one block, and we have only one block. We don't have grid. But in GPU, we have also grid. Okay, we have also grid. And this grid here, you can imagine just like what you see there. So this is going to be handled by block 0. This is going to be handled by block 1. Okay? And then down below there, block 2 in this grid. Okay? And how many of these blocks that you can have? Actually, it's quite a lot. The maximum for X dimension is 2 power of 31 blocks. That is close to 4 billion divided by 2. That means 2 billion. 2 billion blocks in X direction. Okay? That means, do you need for loop here? You can assign, if let's say you got 1 million, do you need for loop? You don't need, right? Okay, let's say, because we know the track of the GPU maximum is 1024. Okay? How many blocks that you need? 1024. And then you don't need for loop at all. So in GPU, there's no for loop. If you look at the code there, there's no for loop. Okay? No for loop, right? Okay? Because it has this grid. This grid. Of course, we have to compute this grid, how many grids that we need, in order to complete this computation. Okay? But here's some limitation. In the X direction is 2 billion, but in Y direction is smaller, is 2 power of 16 only. Is it correct? 2 power 16? Yeah, 2 power 16, which is 64K. So it's a bit less. Okay, in Z direction is also 2 power 16, 64K. Okay, only in X direction is quite a lot. Okay, it's 2 billion. But in Y and Z direction is a bit more. Okay, but most of our problems are normally one-dimensional. Okay, unless we are doing graphics. Graphics is two-dimensional. Okay, but I think our high-resolution TV is it 64K resolution? We haven't reached there yet. Maybe 8K at the moment, right? 8K, I think is within this, right? Okay, even though we got X, Y, Z, it's still within the range. So you do not need for loop when you do image processing in GPU. There's no for loop at all. Okay, because each block you're going to assign to this. But of course, the number of total threads is only 1024. Okay, so it's going to repeat, but the GPU is going to do it for you. You don't have to do it yourself. So you don't have to put your for loop, but the GPU will do it for you. Okay, so even though this dimension is going to be huge, but it can fit. Okay, but of course in this case here, provided that the Y dimension is less than 64K. Now this will not be true when you do linear programming, because linear programming, this one is okay, but this one is not okay, because the Y direction, you can have multiple million of rows, for example. So you can have multiple million rows. So in this case, you have to use for loop. Okay? So in GPU, you can use for loop, but it's very rare. Okay? Because you got the grid to help you. Okay? Unless you exceed that number that I mentioned to you. Okay? Okay, in X direction, if your problem is only one dimension, so it's very simple. It's just computation using this. Okay, before I go into here, let's go to that first, so that we can understand better how it is assigned. At the top there is the global track ID. Okay, is the same as what you see here. Okay, see on this data side here. Okay. At the bottom is the block and the grid. Okay, so the grid is the total of those blocks. So you got 4 blocks there. So the size of this grid is 4. Okay, 1, 2, 3, 4. And inside the block you have 8 threads. So inside the block you got 8 threads. Okay, you can create as many threads as you like in GPU, but the maximum is 1024. You can choose smaller than that. So here it chose to be 8. So one block is 8, and your grid is 4. So 8 times 4, in total you got 32 threads altogether, right? So 32 threads because you got 32 data. You assign each of the thread to each of these data, right? Now, when it goes into the program, you need to compute a little bit. So this is the most confusing part, I believe, is to find out the mapping between the block ID, track ID to the global track ID. And how do you compute it? There's a formula, and that formula is what you see here. There's a formula. And luckily, this formula is always the same. If you memorize this, then every time you use, it's always this. Okay, one thing good about this GPU is this. Okay, you just need to memorize this. But in order to understand, I need to do some explanation. So, what we are finding is this: we want to find this this information that is given when you come into this kernel. Okay, the process, the core of the GPU, run this program. It will be assigned the track ID, but it assigned the track ID in this form. Track ID, okay, here is X dimension. Here is X. Or maybe I'll look at this one better. Okay, the second one. Okay, so you are given track ID in X dimension. And then you're also given this block dimension. Actually, this block dimension is not given. You are the one who selected. So when I run my kernel, I have to specify what is the size of this block, what is the size of this grid. Okay, so I need to specify. So this one actually is me who give it, and then it give it back to me. Right? When I run this code, my thread is going to find out what is the block dimension, which is programmed earlier on before I call this function. Sorry, this kernel. Okay, and then this block ID is going to be that number 0. You see this block ID here? 0, 1, 2, 3. Okay, so as the thread comes in, it will have this information. It will have the thread ID, or the thread index. It's called here. It's called thread index, and the block index. Okay, there are 2 information, and from there you can map it into this global ID. Okay, so this block ID is this number, let's say 1, and then the track ID is, let's say, 3. So block index 1 multiplied by the dimension. The dimension is 8, right? In this case here. So 1 times 8 is 8 plus 3, isn't that this 3 here? And that will be here, right? 11. It is true. 8 times 1 plus 3 isn't it 11? Okay, so this picture that you see here, the mapping from here to here, is this formula. You get it? Okay? So you look at this picture, or you imagine this picture whenever you see this equation. Okay, so basically it's just mapping from the block index number that's given to you and the track ID that's given to you to map your ID to this data number 15, for example. So your track ID is 7, now is block number 1. So your data that you should process is 15. Is that clear? So that track have to go to 15 and grab it. Okay, its track number is 7, but block number 1. Okay, so you grab number 15. So everybody who comes in will have his own block index, his own track index. From that two information, you go and grab the data. So that's how GPU works and how OMP and MPI works as well. Okay? Okay, now, just now it's only one dimension. So how about 2 dimension? 2 dimension also the same thing. When it comes in, it does not have only these 2 information. It has 4 information. The first one is the track index in X direction. And then track index in Y direction. Okay? So, one track, okay, in 2 dimension, 2D right now. This track is going to have 4 pieces of information. It has thread index in X direction, okay, thread index in Y direction, and then it has a block index in X direction, block index in Y direction. It has this 4 information. Okay? And to compute the data, because the data is 2 dimension, right? In X and in Y. So this thread needs to find which data that he has to go and get it and process. So he uses these 2, okay, this one and this one, to find this location. Okay, this location here. And then he uses these 2 to find this location. Then now he knows the data is there. You understand? Okay, it's one track only, it's not 2 tracks, right? One track. But this track has two ID. The X direction ID and Y direction ID. So from this ID, it will know which data to grab. And the computation, luckily, is still the same. Just like what you see here. So you find the row and you find the column. The Y is the row and the X is the column. It's given. Okay? So when the track comes in, this will be given by the GPU. The GPU will tell the track, okay, your track ID X is this, track ID Y is this, and your block ID, which group are you in the block, is this number for X and that number for Y. And then you will go and figure out from that data, you go and figure out which data to collect and then process. Okay, so by doing that, then everybody knows when you enter the program, which data to process. Okay, using this information. Okay. Even though you don't have a for loop, but you have an if statement, and this if statement is quite important. The reason is because when you create the track number, your track number can be more than what you need. Okay, let's say you create a track. For example, in this case here, I got 16, right? And then my data is, let's say my data is 33. I got 16 threads. My data is 33 different data. I want to process using 16 threads. So how many blocks I need inside the grid? How many blocks? 2 blocks, is it enough? No, I need 3 blocks, right? So 3 blocks. So the first block is going to do the first 16. Okay? And the second block is going to do 16. So altogether it's 32 only, right? But I got 33, so there's one left here. And that needs to be done by the other block. The other block is also 16. Okay? Actually it's 16. But I only use one. How about the rest of the 15? The other 15 should not do anything, right? And that's why you have the if statement there. The if statement is to tell the thread, if you're outside here, don't do anything. If you're within here, 33, you do something. Understand? If you're outside, don't do anything. That's why you see if row bigger than the width, column bigger than the width. Actually, the two-dimension matrix is the same size. This is width. This is also width. Okay? But our number of blocks that we assign may be outside. It's a little bit more. Okay, so the thread that is supposed to take this data should not process it. The thread is there to take it, but that data is not within this width, so it should not take it. You understand? Is that clear? Okay, so if the row is less than the width, the column less than the width, then you take the data. If outside that width, don't take it. Okay, because what we assign is more than what is needed. Okay, the reason is because the block size, when you fix to one number, it cannot change. For example, if I change this 16 thread in one block, it will be 16, 16, 16. I cannot choose like 16, 16, 1. If I can choose 16, 16, 1, then I do not need that if statement then. But because I cannot do that, right? So I have to do 16, 16, 16, even though here I need only 1. So the rest need to not do anything. And that if statement is to ensure that that thread do not do any process. Because if it does the process, it will compute the result, add into your result, and your result is wrong. Okay, so we do not want that to happen. Okay, so that's the reason why you have that if statement. Okay, so to compute this in 2 dimensions, so what we need to do is we need to find the thread ID in X dimension, Y dimension, and also we find, also of course is given, and given to us also block index and block ID, so that we can find that block, the block that is in this small square there. There is one block. Okay, within that block, using my thread ID X in this direction and Y in this direction, I can find my location. Okay, so my global ID is going to be block dimension in X. Okay, multiplied by the row. Okay, and then plus with the thread index. So I'll get this global ID in X direction. Okay, the same thing for the row. I will do it, and I'll get this row. Okay, so I will know what is the where I should store my result. P is my final solution. Yeah? So my matrix is going to be P equals to M multiplied by M. This is a matrix, right? So it's a square matrix. This result here is also a square matrix. So I find my location there, so I know that data should go there. Okay? But as you all know, in order to find the data, this data in this cell, because it's a matrix multiplication, we have to take all this element in this row, multiply with the element in this row. Okay, you have to multiply one by one. This cell here is multiplied with this cell. The second cell multiplied by the second cell vertically. This one moved in horizontally. This one moved in vertically. So you multiply, add, multiply, add, multiply, add, and the result is stored there. Okay? Alright, how do you find the row? The row is found by using the Y dimension, information of Y dimension. How about the column of this n? You find it by using the X dimension. So you know the X dimension and the Y dimension. And then You multiply, and then you put it there. And this is what the code is doing. You see this K here? K0 until K the width, because this is the width, alright? So K is the loop that you go into each cell one by one. Okay? You go into this cell, and then you go into this cell, you take that 2, you multiply. See? This one, multiply with this. The cell in the M, cell in the N, and then you multiply. And then you put into the value. And you keep on adding until you got the final value, and then finally store into the location. The location is row multiplied by width plus column. Why? Because the row is a number, right? Let's say this row number M. The position here should be row multiplied by the width. Okay? And the offset here is column plus column. That's why it's row multiplied by width plus column. Okay? I hope that you understand this, because that is how GPU, of course, this is one way to solve the problem. There are many ways to solve it, and this is the easiest way to solve it. Okay? Okay, just now I showed to you it's only X and Y dimension, but if you have 3 dimension, it's the same thing. Let's say your matrix is 3 dimension, you need to multiply them, you have to do the same process, right? And 3 dimension, you got X, Y, and Z. So the thread is going to have 6 different information. Thread ID, index, X, thread ID, index, Y, and Z, and then block index, X, Y, and Z. Okay, so you got 6 information, and then you use that information to find out which piece of data that you need to process. Okay? Okay, you can view it this way. For example, in 1 dimension, I draw it like that, but in 2 dimension, it looks like this. So this is one block, block 1, block 0, this block 1, this block 2, this block 3. Okay? And that block is in X and Y dimension, so you got in X dimension 0, 0, Y, this is the first one is Y, 0, 0. And then the second is the X dimension, so it's 0 and 1. Okay? So this block 1, 0, this block 1, 1. Right? And then inside there, you got the thread. So the thread has index in X and index in Y. Okay? So this block width is very small, it's only 2. Okay, so basically this sum up how we do it. We have to solve it block by block. You can see that each block here has the thread to process. Right over here, that you see, this block is one of this block that you see here. One of the block that you see here. Okay, so each one of them have the block. So inside they got threads, the multiple threads, but the thread is in 2 dimensions, X and Y dimension. Okay? Instead of 1 dimension, but it's X and Y dimension. Okay, so I finished that part. Okay, let's look at some programming terminology that you're going to use. But before that, you have to look at the architecture first. So in the GPU is the same, just like the CPU. Okay, it has the memory, internal memory. It has also input-output. You can do input-output as well. But the input-output, of course, is not communicating with hard disk. The input-output is communicating with external memory or with the CPU. Okay, and then it has lots of this processing unit. Okay, it has like in GPU, the latest GPU, yeah, more than 2,000 processing unit in single chip. Okay, and our CPU like Intel maybe 16 or 32. Maybe if you are using Threadripper, it's bigger than that, but it's much smaller than GPU. GPU has in terms of thousand. Okay, and each processing unit has its own register and program counter, so they have their own register to run the program. And this input-output is actually for them to communicate with one another as well, okay, which is shown here. Right? So host is your CPU, this is your GPU. Okay? So your GPU has global memory and a constant memory which is shared with the host. Right? And this global memory, it can be seen by all threads. Okay, but when you access it, it's going to be slow. Now, if you want it to be fast, you take a copy, put into the shared memory. The shared memory is just like your cache. It's faster. It's nearer to the processing unit, and it's smaller, but it's faster. Okay, and the register is the nearest to the core, and is the fastest. It's just like the CPU. Okay, the terminology that we use here is a bit different, but the concept is the same. The problem is still the same, just like the CPU. So here is the slow memory, going nearer and smaller to the core. It will be faster and faster. Okay, the scope that you can see here is this. All the thread can see global memory and constant memory. Okay, they can access it without any problem. Inside this block, you got the shared memory. This shared memory only appears when the block exists. When the block disappears, the memory is removed. Okay, so it's not permanent. The global memory, yes, is always there. But the block memory, it come and go. Just like a function call, right? You call a function, the variable is created. When you return from the function, it destroyed. So the same concept here. So the shared memory, you can create, and when you create it, you can use. After that, when you get out from the kernel, you get destroyed. Now, all the threads inside this block is able to see the shared memory. Okay? So there is a scope where the thread is able to see. So if you want the thread to be to see the data, or them to see the data, it must be in the shared memory. Okay? Now, each thread has its own register. This register is only visible to the thread. The rest of the thread is not able to see. For example, this register is only accessible by thread 00 in 2 dimensions. Okay? Thread 10 has its own register. It's not shared. Okay? Whatever that you change here will not appear on the other thread. And of course, it's faster because it's nearer to the thread. Okay? So that is the scope. Now, how about this block here? If this thread is able to see the shared memory here? No, it's not able, because this block has its own shared memory. So this thread is able to see, but this thread is not able to see. Okay? If they want to share, you have to share the global memory. That means you have to put it back into the global memory, and then it's able to see. But of course, it's going to be slow. Okay, so this is scope and the memory name, and its lifetime. Okay, the register, the lifetime of the thread exists, is there. When the thread is killed, no more there. The shared memory, whoever in the block, whatever thread in the block is able to see it, is a shared memory. Once the block is destroyed, it's also gone. Right? But of course, when you destroy the block, the thread is also killed. Now the global one is visible to the grid, and the lifetime is its application. That means when your program is running, your GPU program is running, as long as it's running, is there. Okay, it's never get destroyed. Okay, for the global and the constant. So these are the data that we have. We always use the register, but we never try the shared memory. I don't think we have any exercise on this. I'll see what I can do. Maybe I can create some simple example to show to you how to use this shared memory. Okay. Now the shared memory have to pass in as a parameter in the configuration parameters when you call the function. I'll show to you maybe sometime later. Okay, this is an example of the shared memory. It can be single data or in the form of array. Okay, so if it is in the form of array, you have to tell the size. And how do we tell the size? I'll show to you in one of the exercises. I don't think we have any exercise there. I have to create one. Okay. So basically, this explains what I explained just now already. I don't think I'm going to talk about it. Okay, and we move on to the next slide. Okay, I'm going to revisit what I talked about last time. Remember, I was talking about domain decomposition. We can decompose it by block, or we compose it by cyclic. Okay, cyclic or by block. by cyclic or by block. Okay. So you got your data. Let's say your data is very huge, is 1 billion, let's say 1 billion of this data here. Okay. If you decompose it by block, it means that you're splitting them into chunks like this. If you got 16, let's say you got four threads, then you split them into 4. This whole data here is going to be done by thread number 0. This one is done by thread number 1, this one thread by 2, this one thread number 3. So each one of them is a big chunk because this whole data is 1 billion. Okay? So this is decomposed by block. Another way is to decompose by using cyclic manner. So you got still this many, but you split them into like this. So this is done by thread ID 0, thread ID 1, thread ID 2, and 3. And then you repeat again. So you split them like this. Okay? You apply, sorry, I think so you apply the thread, 4 threads here, and then you move on, another 4 thread, another 4 thread. So this is cyclic because you keep on doing this in cyclic manner. Okay? So this is cyclic decomposition. Of course, you can do it in 2 dimensions as well. Here it shows only 1 dimension. 2 dimension, you can imagine how it looks like. You can refer to the previous slide. Okay, but we got problem when we were talking about the memory just now, right? The global memory, everybody can see, is huge, but the shared memory is going to be smaller, isn't it? Right? So, is it possible for you to do block decomposition easily in GPU? Actually, it's not. Okay? Let's have a look at the picture again. Maybe I should open this as a separate window. Look at this picture here. So you got global memory. This global memory is going to contain all of this, right? And then you got the shared memory, and the shared memory is used by the block. Used by the thread within that block, right? So I'm going to chop it down, this data, and then pass to each one of the thread. Okay? If I do it this way. Can I fit into this shared memory? Okay, here I show you got 2 threads, right? Maybe you can imagine you got 16 threads inside there, let's say. Or maybe 4 threads. So I take these 4 and I pass into this shared memory. Do you have enough space for that? No. Okay, what it can do is that this thread number 00 is going to process this. And when thread number 10, it has to wait. Because that shared memory is full filled with this. You have to wait. Okay? And when thread number 0 is done, then the GPU will copy from the global memory into that shared memory for thread 10 to do. And the rest have to wait. Right? Because you don't have enough memory in the shared memory. Right? So block computation or decomposition is not possible here. Okay? What you can do is perhaps using cycling. Okay? Why? Because you can take this whole chunk inside into the block, and then all the thread is going to do one by one. Thread 0 is going to do this, thread 1 is going to do that, right? And then when it goes to block number 1, block 10, it's going to take this block. Okay, it goes into here, and then all the thread is going to work on it. Okay, that's what it means by changing your program in order to make sure that your program, your system matches your architecture so that your system can process it. Okay, so this is okay, you can do it, but you do not have enough memory. So everybody is going to read into the shared memory, and when it is not available, the other thread has to wait. Okay, wait for one another. So you can do, but it's going to wait, and waiting is bad. What we can do is this: you read them chunk by chunk. Because one chunk here is one block, we call it block, and each of the thread is going to process. Okay, process this data here. All right, and then you move on. So you take this chunk first, process it, and then you move on to the next chunk, and then all the thread is going to look at this on-chip memory. Okay, this global memory is slow. This on-chip memory is fast, and it's smaller. Okay, so that is a concept that we're using, but in GPU we don't call cyclic or whatever, we call tiling. Okay, there's another new terminology. If you heard tiling, it means this cyclic decomposition. Okay, you use this analogy, you got carpooling or whatever, so I'm going to skip that because I already explained, and I think you understood from what I explained to you here, so I'm going to skip that. So in this case here, as you can see, all the thread needs to make sure that they use the same data and they work on the data at the same time. Okay? That means if I have this data here, if you have to work on it, you have to work on it. Right? You cannot I have to go and get this other data from another place here in order to process it. If you have that kind of situation, then this will not work. Okay? So if one have to sleep, work, and have dinner, so the rest of the thread also will be doing the same thing because you have the same data, right? If your situation is like this, then it will be a little bit more difficult, okay? Because maybe thread number 2 require the data from here in order to process it. So this will not be good. You have to adjust your data such that the data that you read is all inside there, okay? So these are the problem that we face. This one tile, and the other tile, and the other tile. So here, thread 1 is using this, but thread 2 at the same time you use it here, different time. Okay, so this is bad, this is good. Okay, because they use at the same time. And when you reach here, they also use it almost at the same time. Okay. Okay, since we have multiple threads that is running, one problem is we cannot stop them, or we cannot tell them, okay, you wait. Okay, they were going to run at their own speed. Okay, if let's say they finish, they can move on to the next one. They finish, they can move on to the next one, right? Because these are all thread 0, right? But sometimes you have to wait, right? Because your shared memory is small. So if let's say this thread is working on it, right? Sorry, the thread memory is here, the shared memory is working on this data here, right? And if let's say this thread is moving to the next phase, so it has to, the GPU has to read new data in, but this shared memory is still used by other threads. So thread 0 has to wait. Okay? So in that case, we will need to use barrier, just like what we have learned in OMP and MPI. Okay? Before the thread in this block move to do this block of data, where it has to read the data from global memory into this shared memory, now it cannot proceed, right? You have to wait. Okay? Because some of the thread is going to be faster than the rest. So you have to synchronize them by using this barrier. This barrier will ensure that the one that is faster, let's say for example here, he has to wait. The one that is slowest, so here, he still can go on. And finally when he reaches here, everybody will start to begin at the same time in the next phase. So everybody is going to start processing this data at the same time, starting from there, right? Okay, so you have to deal with this when we have this kind of problem in GPU. Okay, it's the same thing as OMP and MPI as well. Okay, so these are the things that you need to do. First, you identify what are the global memory that you want to use. Then you load it into your shared memory or on-chip memory. And then when you have to move, because your on-chip memory is limited, so you must make sure that all the thread finishes processing the data before everybody moves to the next phase, so that you can load the new data, overriding the old data. Okay, so you have to use barrier. Okay, and then you must make sure that all of them process at the same time. Not like one process, the other one waiting for something. No, you have to make sure that all of them work. When they work, when they rest, they all rest. Okay, or like what you saw just now. When they sleep, they sleep. When they do the work, they work. Or take the dinner, they take the dinner. Right? Okay, you do that in synchronization, and then you move on to the next data. If you can manage that, then all of them will be working on the data and finish the job. Okay, this is the example of image processing, color image, RGB, and you convert it into, I think, grayscale, is it? Yeah, converting into grayscale. But before that, let's have a look at how the image pixel appears on the screen first. So each pixel that you see actually is composed of these 3 pixels. Very, very tiny on your screen. Okay, and one pixel has 3 colors, R and GB, and they can produce different intensity. The intensity is encoded inside the byte. Okay, that is holding the intensity of the color, respective color, R, G, and B. Okay, the color is actually, if you open it up, and actually it's not just OpenCV, because I use OpenCV to do this exercise. You can have a look at it later. But because your memory is also stored in that order as well. So B start first, even though I say RGB, green, blue. Green, blue. Okay, we always say this, but then when it is stored inside the memory to be displayed on your console, it is stored this way. It's stored blue first, then green, then red. Okay, so it's stored in this manner. So this is the lower address. Okay, this is the higher address. Okay, the lower address store the first byte, store the blue intensity. The second byte store the green intensity, and the third byte stores the red intensity. And this 3 byte is 24 bit. Okay, so you need the 24 bit in order to generate a pixel color on one dot on your screen. Imagine how many dots that you have there. So that many, that much of data that is needed to store the image on the screen. Okay, so your monitor actually has memory as well, and it has this much of memory. Okay, so let's look at how we do the image conversion. Here is an image color conversion. We want to change the color image. I know that this looks a bit reddish, right? Actually, it's 3 different colors, but because this picture, I think, is 1960 something. At that time, the camera is reddish in color, so that's why the picture is this. Actually, we shouldn't be using this picture. We should use a modern picture, but never mind. This is the picture that I have. So we're going to use this to turn it into grayscale. And the grayscale formula is very simple. It's this. You take 21% of red, 71 of green, and 7% of blue. You combine them, then you produce the grayscale color. Okay? Actually, our eyes is very sensitive to green color. Okay, so that's why green is higher intensity, right? And the rest of the color is actually not, our perception to this color are not so good. Okay? So if you use this formula, okay, you can combine these three information here, 3 byte into 1 byte, 1 color. Right? So this is going to be the grayscale, which is from black, which is 0 intensity, 255 will be 1. Okay? So how do you do the conversion? Because you need x, y dimension, right? So first thing is you have to pass in the image first. So the image is going to be gray image that you see there. That's the output image, gray image. And the input image is the RGB image. Okay? The width and the height is the 2-dimensional image in 2 dimensions. So you got this 2 dimension, this is the height, this is the width, the width, sorry. Okay, and each pixel in this RGB, there are 3 information. First is blue, green, and then red. Okay? And the width here is how many of this set, not how many bytes. Okay, so this is considered as 1 set. Okay, if the width is 10, so you got 10 sets of this, right? And you have in x dimension and y dimension. Okay. Now you need to, when the thread comes in, when you configure, of course you have to do 2 dimension. You have to configure the block in x dimension, the block in y dimension. Normally we choose the same size. Okay, the same size. And we have a limit. So you got x dimension, you got y dimension, right? And how many threads that we can create for this x and y? Maximum it cannot exceed 1024. Okay? So in x dimension, the number of threads is, if you want to limit and you want it to be symmetry, here is 32, here is 32. You multiply that, you get this number. Right? Okay, so you cannot exceed this if you want it to be symmetry. So in x dimension, the number of threads in a block is only 32 threads. Okay? And here 32 threads. Altogether, we got 1024 threads in this square. If you multiply 32 times 32, you get this number. Okay? Alright? So each one of them is going to be working on it. So it's going to be like this, 32, 32. Okay, so this one block. Okay, and this is another block, 32, 32. This is another block, 32, and this is also 32, and so on and so forth. Okay, so it's going to be block by block. Okay, so imagine like that. And every time they comes in, they have to find the data that they need to process. Because when they come in at time, they will have their own thread ID in x dimension and in y dimension. Not only that, they also have the block ID as well. So the block ID in x dimension is 0. In y dimension is 1. Sorry, 2 is 0, 1, 2. So this block is 1, 0. Sorry, 2, 0. Okay? 2, 0. This block is 1, 0. This block is 0, 0. With the block here, the block ID is 1, 0. The block ID here is 1, 1. The block ID here is 1, 2, 1. Okay, and so on and so forth. So it has its own block ID and its thread ID in x and in y dimension. Okay, so you can imagine that the thread ID is the location here. Okay? And you use the block index number to compute the location, the global data at that location. Okay? And this x and y this x and y cannot exceed this width, cannot exceed this height. Okay, that's why you see this x and y must be within this range. Okay. Now what is inside there? Inside there is very simple. First, you compute the location of that pixel in this picture. So you got the x and y, right? So you got the y. Sorry, you got the global, I should call global x, which is here. Let's say this pixel, and then the global y, which is this pixel here, right over here. The data is there. Okay. So the global x, global y is computed here. Okay, the x and y, I call it global there, but here it's actually x and y. Okay, so x and y is the coordinate at this point there. Okay, so you take the x and you got a y. Now you want to get to the data. Okay, because this image here is also actually here it shows you 2 dimensions. The actual image is 1 dimension. Okay, so this is row number 0, which is this row here. Okay, and row number 1 is right over here. Okay, row number 2 is right over here. Okay, so it's linear, but here we put it in 2 dimensions, but actually it's linear, right? So we use this formula here, to find the offset inside this linear memory. Okay, so we know that we have the x and then also the y, right? So we need to multiply y, multiply by the width. Okay, and then x is the offset. You add it up. Okay, so you find the position here, and then you grab that data. That is the offset. Okay, and then you grab the data from the color image. Now remember, the color image is red, green, blue. So it's 3 bytes, right? Because each is 1 byte, is 1 byte, is 1 byte. So you need to multiply by 3. So the channel here is actually, how many color channels are here? You got 3 colors, right? So you multiply by 3. There you can see that channel is 3. Okay? So you multiply by 3 because in color you got 3, 3, 3. One set is 3. Okay, but in gray scale is only 1 byte. Okay, so the RGB offset is gray offset multiplied by 3. Right? Okay, and then you get to the RGB memory. You grab the actually this one is wrong. Okay, this one by right should be blue first. Okay, I know that you can simply put anything, but I'm sorry, I cannot change that. I cannot change this color. Okay, just leave it first. I'll change it later. Right? It should be blue first, then green, then green color. Okay, so this is not right. If you want to use this code in later on, you cannot. You have to change because this one is not right. Because the blue comes first, followed by green, then followed by red. Okay, so you have to make changes if you want to fix this. Okay, so you find the red color from the RGB, the green color from RGB. You offset it because offset 0 is actually is wrong. This one is blue. Okay, start with blue first, green, and then red. So this offset 0, offset 1, offset 2. That's why you plus 1, plus 2, plus 3. Okay. Okay, once you get that data, RGB, and next what you do is you use that formula, the formula that is shown. And then you go to the grayscale offset, you go to that memory location, and then you put that data there. Okay, so this grayscale will enter into this grayscale. So this grayscale image, the size is actually 3 times smaller, right? because grayscale, 1 pixel, 1 byte. Okay? For RGB color, 1 pixel is 3 bytes. So the picture here, the size here, is actually 3 times smaller. Okay, 3 times smaller than the color. Right? Okay, so you once you put into that, then you can actually view the image and you see the grayscale color. Okay, if you want to see or you want to try this exercise, of course you cannot use this code directly. I know that the code is there. You have to change this code because I told you already. In the memory, it is stored in this way, VGR. Okay, it's stored in VGR rather than RGB. Okay, where do you get that data? Sorry, that exercise. You can go to here and try it later. Okay, I showed you to you last time, right? You can try this one. Okay, open it up. Actually, I do it nicely for you already, because you just need to put the code inside there. Okay, this one is to load the image. There are 3 images. This one is the start. You just run the program. I mean, run the script so that it's saved into this folder here. Okay, this is start still. Your main program start here. Okay, so what you need to do is just fill in. This one is all done for you. This one I'll explain to you later. Actually, some of the class already touched this argument C, argument B, right? Actually, I get the input from the user. Okay, I find out what files that the user want me to turn into grayscale, and then you read one by one. Okay, the image files, and then you convert one by one, and then you display one by one. So there's a folder here to do that. Okay, and then you finalize the part. Okay, here is the GPU header file, and this is the one that you're supposed to fill in the blank. Okay, so here is the code where you can refer to here. Can refer to this, but don't copy it exactly because this one will not work. I told you already. It should be blue, green, red. Here is red, green, reverse order. Okay, it will not work directly. So you have to make some changes. Come back here, put it there. Okay. So this is the formula. It's the same like what you see. And then you have to fill in the blank here as well. You have to allocate the memory. Okay, you need to know the size. Huh? What is the size of the image? Okay, and then you also need to allocate memory for the grayscale as well. So you need to know the size. The size is 3 times smaller. Okay, so you allocate the memory here and here. Okay, for the grayscale and for color. Okay, and then you copy the color image, only the color. You don't have to copy the gray because you don't have the result, right? So you copy the color from the host memory into the GPU memory. Only the color image, which is the C data. Okay, you can call it any name. I call it C data. Okay, and here is a place where you create the block size and the grid size. Okay. Luckily, there is a formula to calculate this. Maybe I'll show it to you later. The block size, we only have X, Y. We don't have Z. So the Z you put as 1. Okay, the X, Y you have a choice. But when you multiply them, you cannot exceed 1024. You can put 16 here. You can put 16 here. It's up to you. 882. Okay? But I suggest that you pick the largest. You can try any number you want. But when you multiply them, you cannot exceed this number. Okay? So you can choose any number there. But I think I suggest somewhere to use this track of block 32. Okay, so you can use this number. Okay, you put here 32, 32, and then you find the grid size. How do you find the grid size? Very easy. You look at the width, okay, the width of the picture, and then you divide by the block, the track block size. Okay, how many grid? Sorry, how many blocks that you need in the X grid? How many blocks in a Y grid? Okay, so you have to look at the width of the picture and the height of the picture, and the width and the height of the picture is given. Yeah, width and height. Okay, so where does the picture come from? Actually, the picture comes from here. I read it for you already. So I use OpenCV. You can see here, OpenCV. Yeah, OpenCV. I open it here. Where is it? Yeah. Use OpenCV, image read, the file name. I got many files there, input by the user. You go through one by one, and you load one by one into the this matrix image. Okay, so this image, the matrix, will have the blue, green, red inside this image here. It's actually pixel, the pixel image. So it's quite huge. All right, and then here is the way the place I pass. I pass here the color, and then this is the gray image. I also pass in because I want to show later on. So I pass in, but it's empty. This gray image is empty. I just pass in the matrix, but it's an empty matrix. Inside here is this code, and this code is the one that is going to create. So I create the. Do I create it? Yeah, I already create for you, so you don't have to create. So I create it nicely for you. So it's the size actually 3 times smaller. Okay, so I already create for you. How do I know that it's 3 times smaller? Okay, this is CV, OpenCV. 8 here, that means the data is 8-bit. Okay, it's unsigned 8-bit. And it's only 1 dimension. If there's 3 dimension, there will be 3 at the back. Okay, U8, 3. Okay, so 8-bit unsigned 3. Okay, but that one is already done by this image read. So image read will do it for you, so you don't have to do it. But for the gray image, I have to create it. So I say I create, pass in to me is actually empty matrix. So I say empty matrix, create this, allocate memory. The size of the memory is this row and this column. How do I know this row and column? I take from the input image, which is the color image, and then I ask the object, the color image, what is the size of your width? Okay, that width is the columns. Okay, the column set is the width. So I ask the object, the color image, what is the size of the width? So you return me this column. And also I ask from the color image, how many rows that you have? That means the height. So you tell me the height. So from this column and height, I can create this image for the grayscale. So once I create it, I pass it to here. So right now the memory is there, but it's empty. Okay, so QDA color to grayscale is your code down here. Is this one. Okay, you refer to the text just now in order to fill in. Reminder again, is in this order. Make sure that it's in that order. Otherwise, your color is messed up. Okay. So so this size here you can compute because it's given. Okay, the width and the height is actually the column and the row. Okay, is the same number. So you find how many grids here. Okay, you know how to find, right? You got a track per block, and then you divide by the width and by the height. So you know in grid in X direction and grid in Y dimension. So you put in here grid in X dimension, grid in Y dimension. Okay, you compute and then you put it there. Okay, here what do you put in? The first one is the grid information. The second one is the block information. So you pass in here grid size, pass here block size. That's all. Okay, this is the object. You pass in here directly. Okay, this is the gray data. The gray data, which is this one. This is the color data, which is color. Okay. And don't pass in this, because this is the host memory. You have to pass in the device memory. The device memory is created here. Okay, use Q down mellow. Okay, I already named it for you, G data and C data, which is this one. Okay, so you pass in here and here. This is gray, this color, and the width and the height is given. Channel is 3. Actually, channel is coming from channel come from outside as well. So the caller actually pass in the channel. Okay, so channel will be 3. We know that the color is 3. Okay, after you call, when you return, you copy back from the device back to the host memory. Okay, and then you free the device memory. You have to free it. And then when you return, when you come back here, the image, the gray image is there already. Now you use this OpenCV to display on the screen. Okay, is that clear? Okay, it's quite easy. You try it. Now you can see how this image processing is done. Now I want you to try this also. You have already seen that. I already explained to you how to do in GPU. What you need to do next is to try using single track CPU. So you reprogram this again by using single track, do the same process, and then display, and then you do the timing. Okay, and you try to time the GPU and the CPU. See who is faster and how much faster. Okay, so that one I'll leave it to you to try. I don't have the code for the CPU, but from here you can actually do the same using single CPU, right? Okay, the process is the same, just like what I showed you, just that you don't have to worry about XY dimension tracks. Okay, you still have to worry about XY dimension in the picture, but you don't have to worry about the tracks. Okay, so you reprogram it or add the code into here, and then do the timing. Here I don't do the timing. You can add in timing. You can ask ChatGPT how to do the timing using Chronos. Use this time chrono library. Okay, use this. Sorry, no H there. Okay, use this library to do the timing in C++. Okay, and you can use this inside your assignment as well. Okay. So that is for the grayscale. Okay, I have some more time left. Let's move on to the next one. Okay, this one actually is quite simple because, sorry, not this one, this one. It's quite simple because the data is not dependent on one another. Okay, so it can process very quickly. All right, because each of these pixels here, they are not dependent. So the thread comes in and they can process independently of one another. And then we can move on to the next and complete the job. So that is not so common. The more common problem is the data is somehow dependent on one another. Let's look at this example. This one is a bit more difficult because when you want to blur, you have to look at your surrounding color. Okay? Using the surrounding color, then you decide what it should be your color. Okay? And that's how you blur this image. So you look at the surrounding, and then you take the average, and that will be the color on that pixel that you're looking at, right? So if you are looking at more neighbors, then your image will be blurred. So you're going to do this. You take, let's say this is the pixel that you are looking at, right? So you take this value, your neighbor, you add with this value, add with this value, add with this value, add with yourself, add with this value, add with this value, add with this value, add with this value, and then you divide by 9. Why 9? Because you've got 9 values here. So you basically take the average. So this is a total value. Okay? You sum all of them, including your color. You divide by 9, and then you put it back into here. Okay, so your color here is going to be the average of your surroundings. So it's going to be blurred. Okay? If you want it to be blurred, you import more neighbors. So let's say if you want even blurred, you can do like this. Okay, so you are here, Right? So you're going to take this whole thing. Okay? So you're going to add all of them, and then you take the average. The average will be how many then? 5 times 5, 25. So the total value divided by 25. Okay? And this is the blur size. I call it blur size. Blur size of 1. Why? Because the neighbor is the immediate neighbor, one step away from you. Okay? How about the blur size here? The blur size here is 2. Blur size here is 2. How do I know it's 2? The immediate neighbor is this one. This is your immediate neighbor. The neighbor further away from you, 2 steps away from you, is this one. Okay, so this is going to be your neighbor that is two steps away from you. Okay, you can see here 2 steps, this one is 2 steps, this one is 2 steps. Right? This is 1 step away, this is 2 steps away. Now 3 steps away, there's another one, another ring. 4 steps away, there's another ring. So you can imagine if you take the average of all this, the larger the area that is involved, the blurrer is going to be, right? Okay? And the more processing that it requires. Right? Because each pixel has to involve the neighbor. So in this case here, the image of the neighbor is going to be used. So you cannot override into your own data. You have to use another memory. So you find and then you write it into the new memory. Okay? So this is actually dependent on one another, but you can actually overcome it by creating 2 different separate memories. So the original memory, okay, and then this is the result. Okay? If you take the original memory and then you find the solution and then you put it back into this original memory, then you have dependency problem. Okay? Because this image here relies on the previous data, not the new data, right? So it's not possible. So you can overcome this by creating two memories. Okay, the original one you leave it. The result one is a separate memory. So this original one you don't touch. After you find the average already, you put it into this result. Okay, once you put into this result, this original one still maintained. So you don't touch it. Okay, because if you touch it, now this result is going to be wrong because all of them are going to race with one another, right? Okay, so when you're doing this process, you create two different memories. Actually, in my code, I also showed to you how to create 2. So one here, 3 colors, 3 channel. Okay. Okay. So how do you compute it? Okay, here it shows to you how to process. The same thing, if you look at formula, this one is no different from the top. Okay, the column and the row is the same. The way you multiply it is the same. If you have a 3 dimension, the z dimension also the same thing. You just change this to z. That's all. Okay. Okay. Now, how do you find the blur image? Remember, I mentioned to you that you have to go through all this square, right? That's why you got these 2 for loop here. The first for loop and the second for loop. The second for loop goes this way, 0, 1, 2. And the outer for loop goes this way, the row, 0, 1, 2. So it will be row 0, column 0, column 1, column 2. Okay, when you finish the inner for loop, you go up the outer for loop. Outer for loop from 0, it goes to 1. And then you start the column again, 0, column 0, column 1, column 2. Okay, and then you finish the inner loop, go to outer loop from 1 to 2, and then 0, column 0, column 1, column 2. Okay, so it goes like this. From here, here. Right? Now, if we are doing blur size of 2, then it will be like this. The column will be like this also, but the row also will be moving like this. Okay, but here will be 5, here will be 5. Right? So that will depend on the blur size. So you decide your blur size. If your blur size is 1, then it's going to be this. If your blur size is 2, then it will be this. So it's automatically done it for you. Okay? Alright? Just using that 2 formulas. So this code is actually working on. You can try this. Okay, so you got blur row and blur column. So blur row is this outer for loop. The inner for loop is blur column. Right? Okay, for each blur column and row, you find the current row and current column. Okay, and then you need to find the pixel intensity, and then you add it into pix val. This pix val is start from 0. So what you do is pix val is going to carry the sum of this number. So you take this, add into pix val, and then you add all this, and then you divide. Okay, what do you divide? You divide with the pixel. The pixel also start from 0, and you count. Every time you add, you count. So here will be 25, so you count 25, and you divide by 25 here. Pixel divide by 25. Okay? Now, what is this if statement there? Okay. If you look at the image, right? Just now I mentioned to you that this image has neighbor, right? But your image actually have 4 corners. Your image has 4 corners, so you have an if statement to handle that. Okay, let's say for example your pixel is here, right over here at the corner there, and your blur size is 1. So this is not there; it's empty. This one is there, but this one is not there, right? So that if statement is to find out whether you're outside or you're inside. Okay? Whether you're outside here or you're inside. If you're outside, don't count. You don't take anything from there, and your pixel also don't increment. Okay? You only take whatever that is available there. So your number of pixel is less. Huh? The number of adding also is less. Okay? So you understand? I will not go to the math because I don't have enough time, but basically it means that. Okay? So you look at the formula, slowly study it, how actually it select the existing pixel in the image. The same thing here. If let's say you compute this image here, if your blur size is 1, this is not there, so you have to exclude it. This one is there, so that formula, that if statement here is going to allow you to avoid this, only take those that is there. Okay? Okay, so if you want to try this exercise, you can go to here. I think I need to give you. Okay, roughly you should be able to know how to do this. You try it, because I have the skeletal code image as a program for this blur image as well. Okay, have a look at it and then try yourself. Okay, your assignment, please don't make it too simple, because if too simple you won't get good grades. Okay? And you should know whether your program is simple or not. You should not ask me that question, right? Because you should know. Okay, whoever